hear me and see my screen?
Yep.
Cool. So this week is going to be a pretty short meeting, probably. The worksheet doesn't take too long. Has anyone taken a look at it already, or do you have anything that you want me to start off with? Otherwise, I'll just work my way straight through it.
I don't mind just working through it.
Okay, cool. Did you have any particular questions? So I can zoom in on that when I see it.
Not really.
Okay.
Kind of just the whole thing. I don't have questions on the whole thing, but like, I just want to. I didn't have problems, but I want to, see if I got everything right.
Sounds good. So we've got a function that from the left side approaches approaches -1 when x is approaching 2, and from the right side of 2 it approaches -1 also, but f of 2 is equal to 1. So we've got something that 1, 1, 2 looks something like this, say. And then this is how the function basically looks with that hole there, but it's filled in up at 1. So what can we say about this? The limit agrees on both the left and the right side. So therefore, the limit is just whatever both the left side and the right side approach. So it's a, and it just happens to be that the limit as x approaches 2 of f of x is not equal to f of 2. And that just means that we have a whole discontinuity there. Does that make sense to everybody? Cool. So now number 2, if the limit as x approaches 1 from the left side of f of x is equal to -infinity, and the limit as x approaches it from the right side is equal to -infinity, then what would we say about the limit as f of x approaches 1? What?
-infinity?
Yes. 1 second, sorry. Zoom cancel. Zoom just told me that I signed out automatically, but I believe that this is still functioning. Can I get feedback on that?
Yeah, you're good.
Okay, cool. I will ignore that then. Yeah, so you said it's -infinity? That's exactly right. So sometimes you might see something like saying it does not exist. That's because, strictly speaking, -infinity is not a number in the real line. But for our purposes, we're going to treat, when we're talking about limits, we're going to treat infinity and -infinity as numbers. So use this graph to find the limit, find each limit. So we've got the limit as x approaches 3 of g of x. So if we look at the graph here, as we approach 3 from the left-hand side, we approach 2, and as we approach 3 from the right-hand side, we also get 2. So the limit is 2. What about b? If I approach from 5 from the right-hand side, then g of x is approaching -2. But if from the left-hand side, then g of x is approaching -2. And if I approach from the right-hand side, then I'm approaching 3, right? So what does that tell me?
Doesn't exist.
Yes, exactly. And now what'll happen if I so the limit as g of x approaches, as x approaches infinity, this basically looks like we've got a downward sloping line that's going to continue on and on forever. So what's that going to approach?
Negative infinity.
Exactly. So this guy is going to be equal to negative infinity. Cool. My other session took about 20 minutes, but looks like this one will be even shorter. Cool. So the company has a training program. A company training program has determined that on average, a new employee produces P of S items per day after S days on the job, where P of S is equal to 63S divided by S plus 8. Find and interpret the limit as S approaches infinity of P of S. So first off, what is the limit as S approaches infinity of P of S? And so what we're going to look at here is we've got the highest power of S in these lineups. They happen to both be the same. So the highest power of S is just S to the 1 for both of these. And in that case, then the limit as S approaches infinity is just going to be the ratio of the coefficients. So this coefficient of the highest power on the top is 63. And the ratio of the highest power on the bottom is 1. So that's just 63. And again, that's because they are the same power. If we have something that is, so if I were to have 63 S squared over S plus 8, then because S squared grows so much faster than the bottom, than the just single power of S on the bottom, then it's going to approach either positive or negative infinity, depending on if the ratio of the coefficients. And if I were to go off to negative infinity, then I would also have to take into account whether this guy's approaching positive or negative infinity, the lead term there. It really just matters for the lead term as we approach infinity. Everything else basically just doesn't matter because everything's so small in comparison. So what does this actually mean? How should I interpret that? So a company training program has determined that on average, a new employee produces P of S items per day after S days on the job training. So as S approaches infinity, so that's basically saying after he's been on the job for a long time, then the number of things that he produces is going to approach 63. Does that make sense?
Yes.
Would it be like, I don't know, the infinity's kind of throwing me off, like, so it's just like a long time and it's not, I don't know, like, wouldn't that mean it's like the most he's ever going to produce? You know what I mean? Because it's like towards infinity.
Yeah. So actually, it is that's a good like kind of point when you're talking about how this thing models the real world rather than just as like a mathematical thing. In fact, this guy is always going to be less than 63, no matter how big of a number I pick. But as it approaches infinity, it's going to get closer and closer to 63. So we can basically say like, hey, after he's been on the job or after he's been trained for a really long time, he's going to be pretty close to 63. But this doesn't actually tell you just the limit as S approaches infinity. Doesn't tell you how long that's going to take. Because if I had, say, 63S divided by S plus some massive number, then like I don't care how long you're going to work. You're not like the infinity here isn't really relevant, but we kind of pretend that it is. We say, you know what, he's been on the job for 2 years. He's has experiences he's going to get. He's got 400 working days. It's close enough. It kind of functions as infinity for our model, even though, yeah, we are never going to get anywhere close to actually infinity. Does that make sense?
Yeah. So like if this were a test, like what would be like the safest sentence to write? You know what I mean? Like,
Yeah, I would probably write something like, as he gains more and more experience, he will produce around 63 items per day. And also this is the model for the average for a new employee, but I think we can also extrapolate that he's not going to produce the same amount every single day. Some days he'll produce a little bit more, some days he'll produce a little bit less. Something that kind of captures the essence of that sentence will get you full credit.
okay, thanks.
Cool. So now for these guys, the first thing that we should want to do is just plug in the x value, and if it gives us a valid result, then that's going to be our limit. But for these, we're going to get 0 over 0. So if I plug it in on the bottom, I get 9 minus 3 minus 6 is 0, and this is just 9 minus 9. That looks like a 4, 9 minus 9. So 0 over 0 is undefined. So instead, I have to work some magic first by factoring this guy. So how am I going to factor the top? Difference of two squares, right?
X minus 3x plus 3.
Exactly. And the bottom here?
X plus 3, x minus 2.
Yes, exactly. And if you were having trouble, not just the breaking this guy up and saying, okay, it needs to be two things that multiply to -6. So one's positive, one's negative, and then adds to x. So the bigger one is the positive. We already plugged in x equals -3 and found that the top and the bottom were both 0. So that right there tells us that x plus 3 is one of the factors of this. So that can help you out with the factoring process. But now I'm just going to cancel this on top and bottom, and that's what will happen everywhere except for when we get 0 over 0. So that's going to tell us that this function is going to define the limit from either side, because everywhere else those we just cancel. So now I get x minus 3 over x minus 2, and then I can just plug in -3, and I get that's -6 over -5, or 6 over 5. Does that make sense to everybody?
Yes.
Yep.
So this guy right here is also a difference of two squares problem, or when I factor on the bottom. So first things first, if you plug in 36, you'll get 0 over 0, undefined. So then the next thing we'll do is we'll try to factor the top and bottom, but turns out we can just divide the bottom by the top, and then we could factor that as the square root of x minus 6 and the square root of x plus 6. So if we just treat the square root of x as a variable instead of treating it as x, then we get the bottom is a difference of two squares problem. And then I can cancel this on top and on bottom, and I get 1 divided by the square root of x plus 6, which is going to be equal to 1/12. Does that make sense to everybody?
Yes.
Cool. Do you guys remember what rule I said with the previous problem for this one?
The ratio.
Divide the top and the bottom by the highest power in the denominator.
Yeah, you could go through that whole process, be a little bit more formal about it, and then you would get 3 divided by 7 minus 1 over x. And then as x approaches infinity, this guy goes to 0. And that is perfectly correct. I wasn't even being that formal before. I just said, hey, these guys have the same power. Therefore, as x approaches infinity, it's just the ratio of the coefficients, which is 3 over 7. But
Like
yeah,
if you were like if you were taking that like really step by step, would it be 3x over 7x and then 3 over 7, or do you just take 3 and 7? Do you know what I mean?
yes. So like I would just say, hey, we have this rule that if it's the same power, same degree for the lead power of x, then we just get the ratio of the coefficients. But if you wanted to do this really step by step, I would suggest doing what she said of dividing both the top and the bottom by the lead power of x. So that's divide both the top. So we have 3x over 7x minus 1, and then we divide by x over x, let's say. So then that gives us 3, and then we get 7 minus 1 over x. And then if I were to apply the limit to this guy, then the top is clearly just equal to 3, and then the bottom gets 7 minus 0 because this guy approaches 0. Does that make sense?
Yeah.
Step by step there. This guy, you could do the same rule as you did before. The divide the top and the bottom. So if we did that, we would get 2x squared minus 1, 3x to the 4th plus 2. So if we were to divide both of them by x squared, then I would get 2 minus 1 over x squared, and then we have 3x squared plus 2 over x squared. And this guy goes to 0, this guy goes to 0, this guy stays constant, and then this guy goes to infinity. So I get basically 2 over infinity is equal to 0. If you want to go through it in that more formal way, I would suggest, like, you can just say, hey, what's the lead power of the top? What's the lead power of the bottom? If the lead power of the bottom is bigger than the top, then the bottom's going to grow faster. And that tells me that the whole thing is going to approach 0. So either way, if you want to go through the whole process or you just want to use those quick rules, this guy's going to go to 0. We could do the same basic thing here. If we wanted to say, okay, we're going to do x squared, divide both top and bottom by x squared, we get x to the 4th minus x cubed minus 3x over 7x squared plus 9, divide by x squared over. That would be x to the 4th minus x minus 3 over x, all over 7 plus 9 over x squared. And I'm sorry, this should be squared. This bottom thing here is going to approach 7 because this guy approaches 0. This guy approaches 0. But then we have x squared minus x is going to approach infinity. So this is equal to infinity over 7, which is just positive infinity. So if you want to go through that whole process, that works fine. Or I can just say, okay, top one's top has a bigger power than the bottom. And then that tells me that I'm going to be approaching either positive or negative infinity. And then I just look at, as the top goes off to infinity, is that going to be positive or negative? It's going to be positive. As the bottom goes off to infinity, as x goes off to infinity, is the bottom going to be positive or negative? That's going to be positive. So positive over positive is positive. Does that make sense?
Kinda.
Which part doesn't really sink in?
I don't know, like how do you like the numerator, how did you just get infinity from there?
X squared minus x as x goes off to infinity. So each of these guys should still have that limit there.
Uh-huh.
But when
Oh, so
writing,
okay, so you plug infinity. Okay, I get it.
yeah.
Okay.
But if I were to have, let's say, x to the fourth divided by, let's say, plus 1 divided by x cubed, and I'm looking at the limit as x goes to negative infinity, then this guy is going to equal negative infinity because the bottom's going to be negative, top's going to be positive. Top grows faster than the bottom, so that tells me I'm going off to either positive or negative infinity, but I have positive divided by negative, so that's going to be negative infinity. Does that make sense to everybody?
So then when the numerator has a, so I mean when the denominator has a higher power than the numerator, it's 0? Like on D?
Yeah. When the bottom grows faster than the top, when it has a bigger power, bigger lead power, goes to 0.
And then when the top grows faster than the bottom, it's whatever, like positive, negative, depending on what's under what you're taking the limit of.
Yeah, exactly. Depending on if the top and the bottom are going towards negative infinity or positive infinity, or just actually really just if it's going to be a negative number or a positive number as we tend towards. Because if I were even just to have, let's say, divide by -7, then that would also make this go off to negative infinity. So just if the top and bottom are positive or negative, it's going to determine if this is positive or negative.
Okay.
Does that make sense to everybody?
Yes.
Cool. Okay, so use the graph G to identify any x values where G is discontinuous. Also identify the conditions that that does not hold at any point of discontinuity. So just looking at this graph, pretty clearly the point of discontinuity is at x is equal to 5. That's where we jump all the way up here. So it would be something called the jump discontinuity. The solution set for this actually says condition 2. I'm not sure what condition 2 refers to, but this is a jump discontinuity, and it is so I'm just working backwards that this is going to be because that the limit as x approaches 5 from the negative side of g of x is not equal to the limit as x approaches 5 from the positive side of g of x.
Oh, I have it in my notes. Condition 2 is the limit has to exist. So yeah, it doesn't exist, and that's why I say condition 2.
Yeah, awesome. Yeah, exactly. So if the limit does not exist, then there can't be there cannot be continuity. So there is a discontinuity. Thank you. Okay, so identify the intervals where each of these functions are continuous. So this guy right here, the top is always defined. So I really just have to worry about the bottom. The bottom is also always defined, but I'm not allowed to divide by 0. So that's the only thing that can really break for this. So if I look at this guy, when is the bottom equal to 0? So the bottom's equal to 0 when either this guy is equal to 0 or this guy is equal to 0. So we have 2x plus 1 cannot be equal to 0, and 3x plus 6 cannot be equal to 0. So that means 2x cannot be equal to -1, and x cannot be equal to 1/2. And if I want to do this same basic thing here, I can divide both sides by 3. I get x plus 2 cannot be equal to 0, and x cannot be equal to -2. So
And that the answer is those two.
So these are the two discontinuities, but that's actually not what the question is asking. It wants me to find the intervals where this is continuous. So how am I going to change this information to the intervals where this is continuous? So this tells me that it's going to be continuous from -∞ to the smaller one of these guys, so to -2, and then on the interval, so union 2 to -2 to -1/2, and then union that with -1/2 to infinity, because everywhere except for these 2 points, it's continuous. So basically I just break up the real line by taking them out, and that's what this looks like. Or that's what this is, this represents. Does that make sense to everybody?
Yeah.
Cool. What about this guy? Where will this be discontinuous? Where are the discontinuities for this guy?
Nowhere.
Yeah, it's a polynomial. Polynomials are defined everywhere. This guy is continuous everywhere. Therefore, it's just -∞ to infinity, the whole real line. Cool. So now this next guy, when we deal with a piecewise defined function, we have to look at each piece and we have to say, is this defined everywhere on this interval? And then we have to say, okay, does the limit of the left-hand side agree with the limit of the right-hand side? And then also, do all 3 of these intervals together cover the whole line? So let's do 3, 1, 2 there. So this guy covers less than 1. This guy covers less than, or -1. Sorry, this guy covers less than -1. This guy covers between -1 and 3 inclusive. This guy covers 3 to infinity. All 3 of those combined are going to cover the whole real line. So that criterion is good. We're fine there. Next thing we're going to do is ask, are these guys defined everywhere on their individual intervals? 11, g of x is equal to 11 is defined everywhere, so it's going to be defined on the subinterval. X squared plus 2, just like part B, that's a polynomial, so that'll be defined everywhere, and that includes on this interval. And 11, again, is going to be defined everywhere, including on this interval. So the only thing I have to do now is check that it agrees on the boundaries. Also, so part 1, or that first thing, if say that was just less than, then we would have an issue that would cause a discontinuity because it just wouldn't be defined at a single point. But we don't have that. So now we just have to check, do they agree on the boundaries? So if I were to plug this guy in at 3, then we would get 3 squared plus 2 is equal to 11. And that is going to be, so that's the limit as x approaches it from 3 from the negative side is equal to this. Let me just rewrite this. So the limit of g of x as x approaches 3 from the negative side is equal to 3 squared plus 2 is equal to 11. And that's going to be equal to the limit of g of x as x approaches from the right-hand side. So that tells me that it works at 3, and now I just have to check, does it work at -1? So the limit of x from the -1 from the left-hand side of g of x is equal to 11, and that's not going to be equal to -1. So 3 equals -1 squared plus 2. -1 squared plus 2 is equal to the limit as x approaches from -1 from the right-hand side of g of x. So that tells me that my discontinuity, my only discontinuity is at x is equal to -1. So then I'll get -infinity to -1 union -1 to infinity. Does that make sense to everybody?
Yes.
Cool. I have no other material for you. You can ask me any other questions that you have. If not, then if you don't have other questions, you are free.
Thanks.
Have a good one.
Thank you.
Thank you.
Thank you.